Hello world, it's Siraj, and today I'm going to show you how to build your own self-driving car in a simulated environment. And it's actually much simpler than what we've been doing. So recall we've been talking about generative adversarial networks and variational autoencoders and all sorts of stochastic models. This, comparatively, is actually surprisingly simple, which is crazy if you think about it. A self-driving car is simple. No, but it actually is. It's 9 lines of Keras. I mean, the model itself is, and then the helper code. But we're going to talk about how you can build this, and I'm going to show you step by step the entire process. Okay, so here's an example of what it looks like when it's fully trained and it's running in the simulated environment. So I'm super excited. I hope you are. And at the end, I'm going to answer some questions just straight up from YouTube comments. So I'm excited for this. Let's get started. So the first thing we want to do, I'm going to stop this demo. This is what it's eventually going to look like. And now the car is going to crash into the water because I turned off the autonomous feature. Uh-oh. Let me just turn off the simulator. Okay. Simulator is gone. Okay, so let's first go ahead and talk about what this is and what the whole deal is behind all of this. A little bit of theory, and then we'll get back into the code. Okay, so where are we? Where are we? There we are. Okay. So how to simulate a self-driving car is the name of this tutorial. And so Udacity recently open sourced their simulator. So they built a simulator specifically for self-driving cars. So cool, right? It's just for self-driving cars. And it was built for their self-driving car nano-degree students, and they recently open sourced it. So it was built with Unity, which is, if you haven't used Unity before, I would definitely recommend at least checking it out. If I had more time, I would definitely be diving into Unity and building all sorts of cool 3D models that I could play with, and maybe even generating 3D models with generative models. But yeah, it's a great tool. It's very much used in virtual reality and more in machine learning for modeling and things like that. But definitely check it out. But yeah, they built this thing in Unity, and they added a bunch of pre-built scripts. They added a bunch of scripts, and these scripts control things like gravity and momentum and acceleration and all sorts of things that you would think would be in a self-driving car simulation. And you can modify these things as well. These are just values that you could just change in code. But you can find the actual simulator itself right here on GitHub. And I'll also have a link to it in the description and in the GitHub README, but it's a binary file. You don't have to compile it from source. That is like an exe. You just download it. It's like a .app file, and you can just download it for Linux, Mac, and Windows, and then boom, you're good to go. And it's got 2 modes. It's got a training mode and an autonomous mode, and I'll talk about what each of those modes is. But the high level is you just download it and it just works. No dependencies to install or anything, so it's super simple. Okay, so that's what they built. And so let's talk about the 3-step process and how this works. Okay, there's a data generation part, then there's a training part, and then there's a testing part. So the first part is the data generation part. And so what happens is we are going to first look at what NVIDIA did. So to generate data, what NVIDIA did was they took a car and they did the same exact thing that we're going to do. We're going to replicate what NVIDIA and Udacity did. It's the same thing. They built a 9-layer convolutional network, and they attached 3 cameras to the head of a car. Okay, so they attached 3 cameras to the head of a car, and they had a human driver drive the car while the cameras were attached. And all the car had to do was collect data. And by data, I mean the steering let me turn off the sound here. The steering commands that the human driver was inputting, as well as the camera feed. So the 3 sets of camera images coming from all 3 cameras, okay, at the same time. And that was the data generation part. Okay, and so there was images from the center, left, and right cameras with the associated steering angle, speed, throttle, and brake. So there were 4 physics variables, as well as the static images that were coming in. And it saved it all to a CSV, which is what we're going to do. And ideally you have a joystick for this thing, but I don't have a joystick. Ain't nobody got time for that. And just because it's easier, it's smoother with the transitions and stuff, using a keyboard, the WASD keys, is kind of erratic, but whatever. I mean, it works. It works. What you saw was based off of a keyboard training, so whatever, it works. So yeah, so that's for the data generation part. And then there's the training part. Okay, so what the idea is that we have a human driver. Okay, so the human driver is just driving around and we're recording all that data. And then we're going to get a machine to clone that behavior. So we call this process behavioral cloning. okay, behavioral cloning. And to do this, we're going to build a 9-layer convolutional network, 9 layers. In Keras, that's just literally 9 lines of code. And it was based off of NVIDIA's end-to-end learning for self-driving car paper. And yeah, so they trained their model for 72 hours on in a whole bunch of different driving conditions: sleet, rain, hail, all sorts of things, wet, rain, everything. So here's the hardware design. So the hardware design it's obviously a steering wheel, but the steering wheel is attached to a controller. What was the so many acronyms here? The controller area network bus. And so it's feeding in those 4 variables that I talked about, right? And you also have your 3 cameras, and the 3 cameras are all feeding in continuous streams, like just frame by frame, of all the images that the car is seeing. And it's fed into this Drive PX computer, which is essentially like a motherboard with a cluster of onboard GPUs attached to it. And then a solid state storage, which just stores the results. That's it. Okay, so that's the high level idea behind the hardware behind it, and then the software behind it. Oh, and also interesting little tidbit I just recorded from the paper. Instead of inputting the steering command R directly, they inputted 1 over R, and they found that this made turns smoother, and it made the autonomous angles that the car moved independent of the geometry of the car. So if the car was facing left, it didn't matter, or the car was facing right. It's all about what the cameras see, and then using that as the signal to then move the steering angle. So it's independent of the direction that the car is facing. And it sounds counterintuitive, like, wait, you would want that, but you actually wouldn't. And we'll learn more about why that is as we get into this code, okay? So the software design for this code, it's so, it's crazy, because going from generative adversarial networks to this is like, that's it? That's all it takes for a self-driving car? Like, what? But that is actually how it is. Check this out. So here's what happens. We have 2 inputs, right? We have our steering angle, and then we have our sets of cameras, right? So 3 sets of images. Those are our inputs. And so we can think of the problem as a supervised learning problem, right? We have our input data, which are the images, and then our output labels, which are if we could just abstract all of the steering angles into one value, like one binary value, that would be our label. Like, based on what you see, how should you move the car? That's it, right? So we have a CSV just listed of all of those things, right? And at the same time, we have what the car is trying to do. So during the training process, assuming we've generated data, let's say 72 hours of human-generated driving data, we can then compare both of those results together. So we can compute the error or loss between the 2, right? So if we have, let's just say we have the camera angles and the steering wheel from the autonomous car, and then the camera angles and the steering wheel variable from the human-generated data, and then we just vectorize both of those values into one value, and then we find a difference between those values, and that difference is our error, and then we use backpropagation to then update our weights based on that error value. Okay, so it's taking that weight value, or that error value, and then backpropagating it in our weights. Okay, so images are fed into the CNN, and then it computes a proposed steering command, okay? And that is the predicted steering command. And we want to find the difference between the predicted steering command and what the actual steering command would be from the training data, okay? And then the proposed command is compared to the desired command, right? The target label versus the actual output. And then the weights of the CNN are adjusted to bring the CNN output closer to the desired output. And the weight adjustment is accomplished via backpropagation. So eventually, once it's trained, then all you're going to need is the center camera, just one camera. You feed it to the CNN, and then it outputs a prediction, when the prediction is the angle of the steering wheel. Just one output, right? So that's it for training. And then for testing, right? So once we've trained this autonomous model, for testing, we could think of it in terms of a simulator as a server-client architecture, right? The server is going to be the simulator itself. That is our, the app that we downloaded, that little 3D game. And the client is going to be our Python program, what we write. And what it's going to do is it's going to just be a feedback loop. It's going to be a feedback loop. So we can consider it as so this is how we can consider it. It's just the client is piping in steering angles and throttles to the server, and the server is piping back images from the car and steering angles so that it can train it. Right? It's just a feedback loop. So that's the basic idea behind how this works. High level, NVIDIA had the paper on it, and then Udacity was inspired by it, and now I'm bringing it to you guys. So it's just the chain of whatever. Okay, so let's build this thing. Right? Enough talk. Let's build this thing. So the first step is to install our dependencies, and you can do this really easily with just one line of code. There's an environments.yml file, and you can use Anaconda to do this. Okay, so if we look in the environments file, we've got like 20 dependencies here, but you don't have to, as long as you run this one line of code, it's going to install all of these dependencies. Let me make this bigger. All of these dependencies super easily. Okay, so yeah, you got OpenCV, which we all know is a pain to install. So luckily for us, Anaconda is going to make it super easy to install. Okay, so that's the first step. Now, I would do this myself, but I've already installed the dependency here. But what I can do, right, so you just paste that in, and once you paste that in, then you're going to type in, I can show you the command. You say source activate, what was the command? I'll put it in the GitHub README, but then you activate your Conda environment, and it's going to be called behavioral cloning. Source activate behavioral cloning, and then that activates the environment. So you install your dependencies in this container, this Anaconda container, and then you activate it. So then all those dependencies are then active in that shell, in that session in terminal. Okay, so once we have that, then we can generate our data. Okay, where we've got our dependencies, now step 2 is to generate our data. So it's a 5-step process. We're going to install our dependencies, which we assume I've done. Step 2 is to generate the data. So we're going to drive ourselves. We're going to replicate what NVIDIA did with the human drivers. Step 3 is to write the training script. Step 4 is to train it, then have our agent learn or clone the behavior of us, the human. And step 5 is to write the testing script, and then let it run. Okay, so let's go ahead and generate our data. So to generate our data, we're going to have to actually drive this baby, which is going to be a lot of fun. Now, you just double click on the app. I downloaded it. You can double click on it, and then it's got a couple of settings. I set it to fantastic because why not? Of course, the choice. Fastest, depending on your processor, you would want to change this. So I'm going to go ahead and run it at 800 by 600, and it's going to pop up just like that. And I'm going to go into training mode. Okay, so for training mode, I'll just click on training mode, and the controls are going to be WASD. Okay, so just like this. See, this is me driving right now. I am driving the car. Okay, and now I'm going to stop the car. And now I'm driving it again. Okay, so this is human driving. So what we're going to do is we're going to generate data so that we can train our car on that data. Okay, so to do this, we just have to type R, right, to record R. And so then it's going to ask, well, where do you want to save this data to? And I'm going to say, let's save it to the desktop. Okay, let's save it to the desktop and start recording. And now what it's doing is it is recording 3 sets of images from 3 virtual cameras of the car, okay? Assume that the cameras are on top. But what it's doing is it's capturing frames from this game from 3 different angles. And it's also recording the 4 variables I talked about: speed, throttle, and the other 2, the steering angle. There's one more that I'll look at. But basically what you want to do as you train this thing is you want to complete either between 1 and 5 laps, okay? Ideally 5, and look, I'm off track, but let me just stop recording. And so then once you're done, driving between 1 and 5 laps, then hit R again, and it's going to capture that data. So it's going to replay what you've just done, and it's going to go up to 100%. And when it's done, it's going to save it all to a CSV file that we're going to look at and kind of see what's inside of there so we can observe it. So we've got 52%. And in the meantime, let me go to the CSV file and show you guys that. What else can I show you while this captures? Well, it's actually fun to just watch this. Let me see what else I can talk about. The training and testing script. Yeah, we're going to be using Keras, 95%. Here we go. Done. Okay, let's check it out. What did we save here? So if I go to open, and then I go to my desktop, there's my driving log, just like we thought it would be. Okay, so let's take a look at what this is. Let's take a look at what this is. What we've got here are 3 images, right? And it's the first three columns are images. They're pointing to images. And these are the images that it's pointing to right here. This image folder, okay? They're absolute directory values. It shows us exactly where they are. So see, these are the images that they're pointing to, just like that. And these are frames that were captured from the game. And we've got three sets of images for the center, for the left, and these are labeled with the direction, and the right. So we've got three sets of images, and then we've got 4 values here. And these 4 values are those values that I talked about up here, which are which ones are they? The steering angle, the speed, the throttle, and the brake. All 4 values, and these are what I inputted. And see how at the start I wasn't moving, so these are 0 values, but then as I start moving, they're going to change, okay? So that's it. That's it for our data. So what you want to do is, train it between 1 run, 1 full lap, and 5 laps. Okay, so somewhere in between there. So yeah, that's it for our data generation part. Where were we in our process? We were at step 2. So assume that I've generated data, okay, just like that. It would take a while, but I generated data. So the next step is for us to write our training script. So let's write this training script. Okay, so where were we? For our training script, I'm going to say, okay, so we've got 2 files here. We've got a training script, which is model.py, and then we've got a testing script called drive.py. But let's write our training script, right? We've generated our data, and we've saved it to the desktop, and now we want to build a model that will, a convolutional network that will read from this data, and then it will output steering commands. So we've got pandas. Pandas is going to be our data analysis toolkit. NumPy is going to help us do matrix math. We're going to import scikit-learn just so we can split our training and testing data into sets. And then we're going to use Keras as our machine learning model. Sequential, because it's going to be a linear stack of layers. Very simple model. And then Atom for gradient descent. Model checkpoint so we could save our model. And then we've got the layer types that we're going to use. Then our helper class utils, it's going to define our input shape and generate training images. And then our argparse for command line arguments. And lastly, our OS module for reading files. So what I'm going to do is I'm going to write the code for building the model itself, but all the rest of it is pre-written, right? So the data loading parts are pre-written. We're going to load that CSV file that we just created, right? That driving log, and make it bigger. Make it bigger. So that driving log, we're going to generate that data. Or we're going to read from that data using pandas, and then we're going to say, okay, so now we have that in a data frame variable, very easily parsable variable. Thank you, pandas. Then we're going to say for the center, left, and right columns, get those values, and that is going to be our input data. That's going to be our X, right? And then our output data is going to be our steering command. So we can concatenate that into one variable, right? So then we have our input data and our input and our output labels. And we want to find the mapping between the two. This is a supervised learning problem. And once we find the mapping between the two, then given novel input data, which is novel camera images of what a car sees, we could then output the predicted label, which will be the steering command. See, very intuitive, right? Okay, so we've got our input data and our output labels, and then we can split the data into training and testing data. So it's 80% training, 20% testing, and we can define the size of that in our command line argument and test size, okay, which is going to be 0.20. This is going to be this value. And so yeah, so we're going to have our training data and our testing data and our validation data, and we return that. Okay, so, and then we've got the code for building our model, and then training the model, and then the main function, right? So let's forget about these command line arguments. So let's just go straight for the main function. And let's say that for our main function, after printing, whatever our parameters are, we're going to load our data using that function that we just talked about. Then we're going to take that data and use it to train our model. But first we'll build our model. And then once we've built our model and loaded our data, we'll train our model, right? Using those 2 parameters as well as any command line arguments. So this helper function just is for converting a string to a Boolean value for a command line argument. But this training model function is really interesting. Let's first build the model, and then we'll talk about the training model function, okay? So for this first part, we're going to build this model, and it's going to be a sequential model, right? It's going to be a sequential model, very simple model, and we can just pull this straight from the paper, right? The paper told us the parameters with which we could build our network, so we'll use those parameters. We'll use those parameters to build our network. So the first step is for us to say, okay, we want our first layer to be an image normalization layer. Okay, we can totally do that. Our image normalization layer using our lambda function. And the lambda function is going to help us do so really easily. And we'll say, okay, it's going to be, let me type this out and then I'll talk about it. Input shape. Okay, so what's the deal here? So yeah. So this is going to avoid saturation and make our gradients work better. Now notice that these are magic numbers right here, but the authors found that, after training and testing out different values, these were the ones that work best for normalizing the images right when we input it to avoid saturation and make the gradients work better. What do we mean exactly by that? So, the images can be shadowy. They can, depending on the lighting, it can be, certain things could be obstructed, or the hue, or all of these color correction values could be off, and they could give us results that are bad. So we want to avoid that, right? So that's when we say image normalization, what we really mean is we want to format or reshape these image tensor values into values that would give us good predictions in the end, right? So that's it for our first model. And then we've got a bunch of convolutional layers that we can essentially copy and paste once we've written out the first one, because they're very similar. And so the first one is going to have a filter size of 24. Okay, I got you. And it's going to be a 5x5 convolution. Okay, I can do that as well. And then it's going to have an activation function, which is going to be ELU, which means exponential linear unit. So, okay, we've got ELU here, okay, which is more suited for this task than rectified linear units. And we're going to subsample with 2x2 because that's the length of our strides. And then we'll add our closing parentheses. Okay, so that's it. And so why do we use ELU? It's because it takes care of the vanishing gradient problem. That's why. So, okay, so we've got 5 of these layers. Let me just paste that. 1, 2, 3, 4. How many of these? 5. I think that's 5. That's 5. Okay, so then we want to make sure, okay, so what's the difference here? The filter size here is 36. This is how you can just read from a paper and just write out the model directly, right? It's not that hard. They have the parameters, and with a simple library like Keras, you can build a model pretty easily. So we've got 36, we've got 48, 64, 64. Okay, and so then we can remove the subsampling for these last 2 layers, since the stride size is 1 by 1 respectively for each of them. So they'll just end in the activation. And then we're going to add a dropout layer. Okay, so it's asking for 50% dropout. We can do that. So we'll say, okay, dropout. We'll add it based on what the user says it's going to be, and we're going to input 50% later. And then we're going to say, okay, so now that it's dropped out, we're going to flatten the data. And so why do we flatten it? Because we're going to start feeding in a series of fully connected layers. And why a series of fully connected layers? Because the convolutional layers are meant to handle feature engineering. So that means that the image processing part, so the filters, right? So we feed in a set of images, and what the convolutional layers will do is each of them respectively is going to create a set of filters, and these filters are going to be, increasingly abstract, right? So they're going to start off with low-level features, and they're going to get increasingly more abstract. So they're going to be able to detect images, but what we want to output is not an image, but what it is that we want to output is a value. And that value is a single value, and that is the steering command, right? It's a direction. How do you want to move this wheel? So to do that, to get a single value from these high-dimensional image tensors, we have to squash that data. And the way to do that is by applying a series of fully connected layers, okay? And so what's going to happen is each of these fully connected layers is going to progressively get smaller and smaller in terms of the number of neurons they have. And you'll see what I mean here. So it says the first one should have 100 neurons. So we'll say, okay, so this is a dense, which means fully connected layer, and its activation function, like all the other layers, is going to be ELU. And so then what we can do is we can just copy and paste this. We'll say 1, 2, 3. So there's going to be 4 of them in total. Each of them is going to be smaller. So 100 neurons, 50 neurons, 10 neurons, and then just a single neuron. And this one won't have an activation function because it's the last layer, and that's going to output our driving value, our steering value, and say, okay, so it's a summary. So of all of those values, get the summary and then return the model. Okay, And so then we'll say, how much do we have here? There we go. So then return the model. Okay, cool. So, right, so for our fully connected layers, we start off with a big layer and then we want to get progressively smaller. And so the way to do that is by using a model summary. Or by using a series of fully connected layers that get smaller and smaller. And what that's going to do is going to squash our data. So it's going to basically be like a triangle in terms of the number of values in those matrices that are being propagated forward in our network. So it's going to be like, you know, a matrix with 10 indices, and then like a matrix with 5 indices, and a matrix with 2 indices, and eventually one single scalar value. And that is our output. And that's what this is going to do, right? And the line, in the paper they noted this, but I didn't actually document this. They noted that it's not sure where the image part and the steering part begin and end, because it's all kind of connected, right? In terms of what the neural network looks like, but that's part of the black box magic of neural networks. We don't know exactly where one feature starts and one feature ends in terms of where it lies in this abstraction hierarchy, but we know that all as a whole, as a sum total, there is some connectedness, right? So anyway, so that's it for our model, and then once we have this model, we're going to train the model. And so let me talk about this last training function. So for the training function, we're going to say, okay, take the model and then the training data and the validation data. So model and data and train it, right? So to do this, we're going to run the model checkpoint function. And what this does is it saves our model in a checkpoint that we say that we want, and it's going to be model.h5, and then we're going to say, well, what is the loss function that we want to monitor, which we're going to call the validation loss, not yet, but we're going to call it that, and we only want to save the best model, okay, and then we're going to say the mode is going to be auto, and auto mode means the direction is automatically inferred from the name of the monitored quantity. Okay, so that's it for our checkpoint. And then we want to compile our model. So what are we going to do here? We're going to say, okay, well, what is our loss function going to be? Well, there's several loss functions that we can use, and we're going to use a really simple one called mean squared error. What does that mean? So our model is going to output a predicted steering angle, and then we have an actual steering angle from the human driver, given those camera angles, and then we want to find the difference between those angles, and do that for all of the data points that we have, okay, and then sum up the differences. And then, hold on, we want to find the difference, square the difference, add up all the differences, and then divide by the number of them. And that's going to be the mean squared error, the sum of the squared errors, okay? Or the mean of the squared errors, right? And so then we're going to use the atom optimizer, which is gradient descent. Yeah, and so that's how we compile our model, and then we're going to generate some data. So what we're doing here is we're running the fit generator, okay? And so what the fit generator does is it lets you do real-time data augmentation on images on the CPU in parallel to training our model on the GPU. What do we mean by that? Well, we are generating batches of data, okay? While we are generating those batches of data from our training data, like the buckets or the containers from which we train our model in from the huge set, at the same time we're training our model, right? So what this fit generator function does is it does both simultaneously. Okay, so it's super valuable, and then, cool, okay, so then we can train this model, right? We'll run python model.py, and it'll start training on our driving logs. And we want to then, once it's done training, we're gonna write our testing script. So training can take a while. It depends on whether you're using it on the CPU or the GPU, if you're running it on the cloud or on your local machine, but training can take a while, and we can definitely speed it up by running it on the GPU. I ran this thing on my MacBook, and it took about 8 hours to train. So yeah, it all depends on what kind of specification you have, right? So assume that we've trained it. It's going to take hours and hours to train, so we're not going to train it right now, but assume we've trained it, then we can write our testing script. Okay, so let's go to our testing code. So let's check this out. So let's check out our testing code. So for our testing code, remember, it is a server-client model. That's what we're using. We're using a server-client model, and that means that the simulator is the server, and then our client is then the script that we're writing. So we want to think of it like think of it like a server-client model. So we're going to use Flask to do this, the web app framework. So let me talk about the dependencies, and then we'll talk about the code. So the first thing we want to do is define our command line arguments. Base64 is going to help us decode camera images, date time for timestamps. What else? We've got high-level file operations. Socket.io is going to help us work with this as a real-time server in terms of piping commands through event handlers. We're going to use Eventlet for concurrent networking. And then we have more web framework dependencies, and then image manipulation with Pillow. Flask is our web framework, and then Bytes.io to deal with input-output, and of course Keras, just to load our model and our helper class. Okay, so we'll start off by initializing our server, okay? It's going to be a Socket.io server, and it's going to use Flask to do this, and we'll initialize our model and image array as empty because we're going to fill those as we later on. And then we're going to set a max and min speed for our autonomous car, so it can't go faster than 25 miles an hour, and it can't go less than 10 miles an hour. And then we're going to define a speed limit as well, which is going to be that max speed. Okay, so then let me skip this function because we're going to write it, and let me talk about the other functions. So let's go into this main function. So these are the command line arguments that define, where is the model and where are the images that we want to, where the images from the run are going to be saved. So we'll load the model using our load function, and we'll tell it via command line where that model is, and then it's going to create an image folder, and then it can either record the run or not, depending on what we say, and then it's going to launch this Flask middleware, which is going to let our client communicate with the server, and then we're going to deploy it as a WSGI server, right? And that acronym, what was it again? It was WSGI. Let me brush up on my web stuff here. WSGI, it's not CRUD, create, read, update, web server gateway interface, right? We have 101 acronyms. Okay, so what these functions are these are event handlers. And this is why we're using Socket.io as a server, because under the hood for the simulator, it's got the architecture necessary to send commands that we need. We just need to create event handlers to then accept those commands, right? So we don't have to code the server part, we just have to code the client part. So this is really the easiest way to get started with building a self-driving car. This simulator that Udacity released is the easiest way. Obviously there's Grand Theft Auto, which is awesome and stuff, but you can only run that if you're on Windows, and then also, it's got a whole bunch of extra features that we don't necessarily need. But yeah, we could also do it in Grand Theft Auto, but right now this is the easiest. If you're looking for the easiest way to get started with building self-driving cars, this is the way, okay? So we have event handlers for connect, which is going to just send the SID, the session ID, and then we've got a send control, which is going to send the actual commands that our model emits. But then we have the telemetry function, and so that is going to be that's going to be the meat of our code, and that's what we're going to write out here, okay? So we're going to write out this part right here. So we're going to say, okay, so what this does is it's going to make the prediction and then send it. It's going to make the prediction of what the steering angle is going to be, and then we're going to send it to the server, okay? So let's go ahead and write this out. So if data, so we're going to feed this in our data, and then we're going to create an if statement that says if data. So once we've got our data as our focus, we're going to say, let's get the current angle of the car. So we'll say the steering angle. We want the steering angle of the car. Okay, so that's the first variable that we want, and we're going to retrieve it from our data frame. Okay, and then we want the throttle. Okay, so remember, we want these variables, we want these values so that we can manipulate them and turn them into one single scalar value that will tell our car where to go. And then we want the speed, and the speed is going to be a float. It's going to be a float value, and just like the rest, we're going to pull it from this data frame using the key, which is going to be speed, human readable key, and then we're going to get the current image from the center of the camera, from the center camera of the car using Pillow, all right? So we'll say image.open, and then we'll use, this is where Bytes.io comes into play. This is where we use it because we want to convert it from base64, this image, into what we can read directly into our model. So we'll say base64 decode data and then image. Okay, and so then we'll say, okay, so once we have those things, we'll go ahead and do some tensor processing on this image. So we need to feed this image into our network, right? So to do that, we're going to say image let's see what else do we need here. Image, and then so we're going to convert the image to an array, and then we're going to apply the pre-processing step to it, and then the model is going to expect a 4D array. So that's what this image is going to be. And so once we have that, then we can say predict the steering angle for the car given that image. So we're going to say, okay, so let's predict the steering angle using our model. We'll say model.predict, just one line, given the image and the batch size, which is whatever it's going to be. Let's just say 1 for this simple example. And then once we have that, we're going to say, okay, so then given the speed limit, that global value that we initialized, if the speed of the car is greater than what we've set as our speed limit, then change it. Say, okay, well, the new speed limit is going to be the min speed. So then that means slow down, right? And so else, if it's not, then we can say the speed limit is going to be the max speed, right? So we don't want it to go faster than the speed limit is what we're saying here. And once we've done that, then we can say, okay, the throttle is going to be 1.0 minus the steering angle. So this is some magic number territory. This is where guessing and checking comes in. But we'll say minus speed over speed limit times 2, or squared, okay? And then we can send the control using that helper function that we defined before, using the steering angle and the throttle. Cool. That's it for this code, right? So that's it. We pre-process the image, and then we fed it into our model, and then it outputs the steering angle. And then we can use that to then send that control directly to the server via the send control function. Okay, and then it's going to emit that as a packet to the server, and then the server will read that in. So the actual event handling logic is written by is under the hood for the simulator, and we can just send it via our client. That's it. Okay, so then once we have that, then we can compile it, and it's going to run the script just like I did right at the beginning. All right, so to end this, I'm going to answer 3 questions randomly from the YouTube comments, and then we're out of here. Okay, so the first question is, let's see what kind of questions we got here. How to work with multiple data sets. This is a great question, and it's worthy of a video, but essentially there are several ways of thinking about this. One way is you can just combine all your data sets into one big data set using pandas, and that's what I would do. That's probably the best way. That's the cleanest way. But another way you could do it is thinking about it serially. So you'll want to train your model on one data set and then train your model on the next data set. But I would just combine all your data sets into one. 2 more questions that I'm going to read from the comments. What else do we got here? How can I discover a foreign language like Russian? Do you tell me? So this is for the language translation video. So discovering a language is quite a challenging task, but think of it as associations. So as long as you have some kind of labels, and the labels could be a different language, but maybe you're trying to discover an ancient language or discover the rules of some language you don't know, then as long as you have some kind of associations, you can treat it as a supervised learning problem, okay? And I've got 2 language translation videos and links to those in the description of that video. And one more question. Once you have this neural net trained, can it be optimized to run locally, or does it have to be run as is every time? Yeah, you can re-optimize a network. You can use the pre-trained model, or you can retrain it again. It all depends. You can retrain it on your data, or you can use a pre-trained model that someone else has trained. That's it for this session. Please subscribe for more programming videos. And for now, I've got to go clean my kitchen. So thanks for watching.